So we can get started then. Yeah, hi everyone, I'm Jason from University of Pennsylvania Grass Lab. Today I'll share some recent progress on my work on foundation model supervision for robot learning. So I want to start well, I guess the clicker doesn't work now. I want to start the presentation with a quote, right? So this review investigates two recent developments in AI and neural computation, learning from imitation and the development of humanoid robots. All right, seeing this quote, how many of you guess this quote is coming from, let's say this year or last year?
10 years ago?
Yeah, make a guess. Shout out some numbers.
5 decades ago.
5 decades ago.
You guys have it boxed in.
It's like the 90s.
Yeah, so this is actually the beginning of this really nice review paper called Is Imitation Learning the Route to Humanoid Robots in 1999. And I feel like this review really resonates with the field of robot learning today as well. Because this is how robots look back then, Honda humanoid, right? So fast forward 25 years to now, we have all these fancy, much better looking humanoids. I'm doing very complex tasks, again, with imitation learning mostly. And since 1999, not only humanoids have made a lot of progress, but certainly there's also a lot of progress in the underlying imitation learning algorithms as well, such as the ACT algorithm or the diffusion policy algorithm. And if you scale these kind of models up a lot, when you have a lot of data, if you're Google or if you're a well-funded startup, you can actually solve very, very interesting tasks, such as tying shoelace or doing laundry as well. So it seems that if we scale up imitation learning with humanoids or with dexterous robots, we can actually achieve a lot of complex tasks. But is that really? But do we actually have enough data? Is imitation learning scaling up the final solution for robotics? This is a very nice slide from Kevin Black. You see that the largest robotics data set today, such as the OXC data or the data collected by physical intelligence, are much, much smaller than the number of tokens or data sets required to train even a foundation language model GPT that existed more than 5 years ago. So clearly it seems that if we're only scaling up imitation learning with data, given that imitation learning is very data hungry and they don't really generate well out of distribution, the only way to generate value seems to just scale this up. And it's unlikely that this will be the final solution to solve robotics. So when we come back to the chicken egg problem robot learning, a lot of us are concerned with, what I just demonstrated is the approach of doing this, where you have this chicken egg problem where you don't have enough robot data to have good robots, but you don't have good robots, so you can't collect enough robot data. So let's just make the investment on the robot data even bigger, have more humans, more resources to collect it. But I'll present an alternative view on how to scale up robot learning, especially thinking about a different kind of loop that I will think make robots much more autonomous so they can collect more data and actually make robot learning, like generalist robot, a dream true in the future. So the solution I will take is that instead of just thinking about the loop between robot models and robot data, let's think about where foundation model, generally models that train on a lot of data and the likely non-robotics data can come into the picture. So the solution I have is that we can use foundation models like GPT or vision foundation models or data sets like human videos to first supervise robots to do a bunch of different tasks, providing necessary learning signals such as reward functions, value functions, training environments, whatnot. So robots become more autonomous, more capable. So it's no longer robot, but it's robot plus plus. I mean, when you have robot plus plus, then of course, these robots can start collecting more robot data for you. And once we have these data, they can first of all make the robots better, right? But what's more important is that we can use the same data to go back to the underlying models that were not yet really trained with robots data at all, right? So as these foundation models are even becoming more active, more embodied, then I can imagine they can provide even richer and greater supervision for robots. So robot plus plus maybe in 2 years becomes robot plus 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 plus. And then this loop will continue and we can actually make robots much more capable in the physical world. So my research so far has really focused on the arrow going from foundation model and diverse data, thinking about novel algorithms that can train new and leverage existing ones from non-robot data sources to provide scalable supervision across diverse robot embodiments, tasks, and learning algorithms. Because at the present moment, we don't have enough robot data, so we should consider using structured prior from outside other source of knowledge to really bootstrap the robot learning process. And in particular, I'll provide a high-level overview of some of the different pillars of my work. So the first kind of approach I've exploited is using large language model code generation to provide training environments to automate sim-to-real of very complex robot tasks, such as spinning pencil in simulation and making a robot dog walking yoga ball in the real world. But sim-to-real, in my opinion, is only a source or a way of initializing robot policies. At the end of the day, robots need to be deployed in the real world. So they need the ability to adapt and learn continuously in the real world as well. So that's where the second pillar comes in, where we can mine useful supervision from human videos. And in this particular case, learning very general value functions that can be used to guide robots to solve diverse downstream tasks. Like for example, we can teach a spot robot opening a drawer autonomously in the real world using such approach. But finally, human videos is only a very small portion of all the internet scale data that's out there. What if we can, again, now leverage not just video data, but also just more broadly vision and language data together? Then I think we can make step towards a universal value function that can provide a guidance and dense progress estimation that can allow robots to solve or make progress towards any task in the physical world. So I'll briefly talk about some of these works and with special attention on some of the newest work in the first and the third category. And if you have any question or want to chat with me on some of the other works that I only skimmed through, yeah, feel free to find me after the talk and we can discuss as well. Okay. So in the first pillar, exhibit 1, using large language models to automate sim-to-real. So sim-to-real has seen a lot of successes in recent years, right? We can teach robots, let me see if these videos will play, to rotate cubes, traverse different terrains, and do championship level drone racing. But what's really important to understand is that behind the scene, all these successes required a lot of manual design and domain expertise. Like for example, an engineer has to manually tune these reward functions, and besides reward function, they also have to design environments and design domain randomization. So even though sim-to-real is a very good way of scaling up robot skill for, let's say, a single task, it's actually a very manual and human-intensive step. So the question that I wanted to answer about a year ago is, can we actually automate a lot of these design that humans have to manually do using some capabilities from the large language models, right? Providing these necessary training signals from the model that's not made for robots to bootstrap the robot learning process. So the first work that explored this is called Eureka, where we combined large language model with the idea of iterative search to design reward function code in simulation. So the idea is very simple. Once we have some specification of the environment, we can ask the LLM to generate a bunch of reward functions. We can try them out in simulation, right? And then based on whether or not each particular reward function is promising, we can query the large language model to generate more reward functions like it. So iteratively coming up with more and more reward functions to optimize for some ground truth objective for the task. So this method of using large language model in research is actually quite scalable. And you can think of it as a way to leverage test time compute to really scale up robot learning and accelerate the procedure. So we did a bunch of benchmark tasks on existing simulation environments, and using 5 iterations of search, we can discover dense reward functions, reward shaping, that can exceed dense reward functions written by humans. But what I think is really interesting in this case is that it's not just about solving existing environments, doing so better than maybe what a graduate student can potentially do, but rather it also enables us to go beyond what's already out there and solve even more dexterous tasks. There has been no method that's demonstrated this kind of dexterity before, right? So this just shows to showcase the capability to use foundation models to supervise robot learning. Sometimes we can automate the laborious things that humans have to do, but often we can also go beyond what's already possible and really test out new capabilities. And so far, we have shown how to use large language models to automate reward function writing simulation. But if you want to get a robot to truly work, it's not just reward functions you have to automate. There's also a lot of physics parameters you have to randomize. And doing this is, again, another labor-intensive step for the human engineers that must understand, okay, friction and payload are important for doing tasks like this. So, follow-up work to Eureka presented in RSS this year, we took the algorithm a step further to also generate valid domain randomization parameters. So the intuition is that even though the large language model hasn't seen the exact task, just by reading its task description and understanding the space of all physics parameters it could possibly randomize, it could use some common sense knowledge in its training data to infer, okay, to make a robot dog walk on yoga ball, it's probably a good idea to randomize friction of the ball and also the friction on the ground. So that's the key idea in this work. And we're able to use this idea to first fully automate the entire sim-to-real procedure in the design aspects, including reward functions and domain randomization parameters. But solving these, standard, I suppose now standard tasks like walking and rotating a cube is not super interesting. We took a step further and designed a new task in simulation, which is making a robot walk on yoga ball. And we demonstrate that this algorithm can actually generate sim-to-real configurations that can actually transfer to the real world and doing pretty, that's just an interesting thing. Like if you look at the video at the top left, I guess it's glitching now. You see that the robot is going from a grassy surface and going over a curb, and the robot can still stay balanced on it afterward, right? And we have more videos where instead of a human that's providing some safety mechanism with a leash, we just tie it to a pole, and you can also stay balanced for about 5 to 10 seconds. This is showing that with a large language model that's doing a lot of the heavy lifting, right? It allows us to solve new tasks much faster than before and providing, freeing up, robotics engineers and graduate students time to do actual research instead of doing hyperparameter or simulation tuning. So that's the vision that I have for using foundation model to provide scalable learning signals across tasks and across embodiments. So far in the Eureka and the Dr. Eureka work, we designed aspects of the environment to solve a single task. But how do we scale up to a repertoire of tasks, right? Where we want the policy to not just do pen spinning or just yoga ball, but let's say a family, a distribution of related tasks. So typically for skills, there's a hierarchy of them. Now, skills build on each other. Some of them are easy, and learning them first is necessary to get to harder and harder skills. So in a follow-up work presented last week at Coral, titled Eurekaverse, we instead began to tackle using large language models to now generate the environment curriculum as well. So on this paper, I serve as the last author, and the first author, William Liang, is on the PhD market this year. So he's really good. You should hire him. Yeah, so in this work, what we wanted to do is that we're first making an observation that if you want to teach robots complex skill, you want to train them in a curriculum. And again, like rewards and domain randomization, it requires manual design. So a researcher had to come in and design, let's say, these different courses to teach robots how to do parkour skills in the real world. And what's really interesting is that environments also share similar programmatic structure as reward function or domain randomization. So here is an example where this course corresponds to this, huge chunk of code. And with humans, with our limited patience and time, we could only design a couple of them and test them in the real world. If they work, that's good enough, right? It's really hard for us to scale this much code by a lot. So in this Eurekaverse paper, following the idea in Eureka, we asked the large language model now to generate environment code, to basically generate different, let's say, training terrains for the robots. And what's important here is that we have an adaptive mechanism where, based on how the policy is currently doing on these environments, we'll selectively generate more environments like it, or discard the training environments is too difficult. So the environment curriculum generated by the large language model is also adaptive to the agent's current capability. So what's happening is essentially the large language model, code generation, and the reinforcement learning agent is trained on these environments are co-evolving until the agent is really, really good and can do really complex parkour skills. So here's our benchmark evaluation on some held out parkour courses. You see, if you just randomly generate terrain or environments, given some programmatic specification, you can't really do anything. You quickly plateau. And here's if you train on the human design ones from the prior work. So that encompasses all the environments that humans manually design. But if you use our algorithm, Eurekaverse, to iteratively generate environments as adapted to the agent skill, what we see is that, even though initially the learning progress is not as good as the human ones, which is to be expected because LLMs are not really designed to design parkour courses. But as time goes on, the diversity and the adaptability really takes over and allows the policy that's trained on synthetically generated environments to exceed the policy that's trained on environments that humans can manually design. And here are just qualitative illustration of the environments progressing over time. So in the first iteration, here are the program or environment code that LLM generated, right? It's not super difficult. And after training on these, the agents can do pretty well, but I'll just fast forward to iteration 2. So now the LLM's starting to generate some gaps in the middle, right? So if the agent goes underneath, gets stuck, then game over, it has to be respawned. And eventually at level 5, after 5 iterations, it's really generating really tilted ramp and with really big gap, right? So it's showing that it's progressively generating harder environments that can make the agents learn better. And in the paper, we have a lot of ablations to show both the curriculum and also the adaptiveness to the agent's current progress are really crucial for this method to scale up and teach really complex skills.
How do you decide the complexity of the environments?
Yeah, so if we train agents on environments, if the agent just doesn't solve an environment at all, that's a pretty good signal that that environment is too hard. We need to make it easier and vice versa, right? So we have that kind of mechanism in the loop to make sure the LLMs are always generating environments that's not too difficult, not too easy, but just right for the agents to continuously learn. Okay.
How do you represent the mesh or the environments?
Yeah. So like there's like a language, basically it's like a 2D height map that determines how the ramps, how the obstacles look like. And that's really taken from the extreme parkour prior paper that designed this parkour task. Yeah, one more question. Yeah.
Just a quick question. Do you have a mechanism in the environment design process that keeps the generations from being too easy? Like there's the mechanism you have for like, if the agent kind of fails, then you kind of remove them. Is there a procedure for like, how do you ensure there's not too many easy environments getting
we also have a procedure to, remove or not continue training on the easy environments, right? For easy environments, it's like you are able to complete a course, right? Then that's a good signal. You don't need to train on it any longer, right? So it's like that. And, just by scaling up LLM in the search, we can actually design interesting environments to allow the robots to learn and see. Here you have to like jump a ramp that's a lot higher, and here's a slippery surface, and it's able to complete all of that together. And here's like a real course that we designed in our app, where the robot has to sequence together all these skills, and maybe these kind of skills have been demonstrated in prior works, but what's really interesting here is that its skill entirely is supervised by large language models. And here, you saw the yoga ball making a cameo appearance, right? And this is clearly not in the generated terrains, just to show the adaptability as well. And since in the real world, we have to use vision to solve the task, we try to throw in objects at it and also dynamically changing the course on the fly to show that the robot can, in a short amount of time, adapt to like a new gap that's in front of it on the process, showing that the robustness and generalization we are able to get by purely training on synthetic environments, right? So the conclusion here is that by scaling up LLM in search, we can do automated sim-to-real skill learning. But I think there's a lot more to do here. Large language models is not the only generative foundation model we can use. There are now foundation models for 3D assets, for videos, etc. And how can we combine them all together to come up with the best initialization that we can get without incurring any real-world robotic interaction? So once we start in the real world, it's already initialized at a good point. and we can continuously train robots to do better. Yeah, so we also have a newer work that I'm not going to talk about now that scales this similar kind of idea to do sim-to-real manipulation. Right, so like I alluded to so far, once we have this pre-training stage using foundation models with a lot of signals, I think robots still need to learn and adapt in the physical world, right? Because then, there's never a perfect policy, if you will. There's always some room to improve in the real world, given the messiness of the real world and a lot of, extra noises, right? But then the core challenge is, in order to learn and improve in the real world, we need to provide, again, learning signals that's acquirable from real world sensing modalities, for example, vision. We call that in simulation. You can just write a piece of code because you have a simulator and you can have the ground truth state. But now we need to do this from vision. So the question is, where do we get this data when we don't have enough real world robot data? And what is the right thing to learn here? So the solution I propose is to leverage in the wild human videos, right? So human videos are a form of actionable data that's much more readily abundant than robot videos. But then the question is, what is to learn? So given the huge embodiment gap between humans and robots, there are prior works, including some from me and my collaborator, on learning actions from human videos. So that is just another way of initializing the real world robot policy and doesn't answer the critical question of how can we allow robots to continuously improve. Right? So my answer is, from human videos, instead of just learning actions, that's a very coarse guidance or coarse initialization for the robots. Let's mine let's mine useful learning signals from them instead. So the solution I propose is to learn what I consider this universal value function from in the wild human videos. So meaning that you learn a value function that takes in the current observation and some goal specification like an image, and then we can zero shot produce dense and meaningful value curves for real world robotics tasks. And with a value function, there's a lot of applications you can explore, right? Really agnostic to the underlying policy learning methods. You can do planning with it. You can do reinforcement learning with it. You can, upweight, downweight transition or demonstrations and imitation learning setup. You can also do exploration. So the applications is pretty abundant. And so the question is just, how do we get our hand on this kind of universal value functions from just human videos? So the idea is that we can learn visual representations that implicitly encodes the value function in its embedding space, right? So, you have a neural network feed that takes an observation goal, and implicitly it will compute, treat the representation's embedding distance as a negative value. And here, value just means the temporal task progress, right? So it's pretty agnostic to the semantic meaning of the task, because in every single task, you have to go from 0 task progress to, finally completing a task. So the algorithm to make this happen is a little bit involved, but it's taken from my prior work on developing goal condition reinforcement learning algorithm that can work from action-free data. Right? Human videos don't have actions for robots, so to apply this, we need reinforcement learning algorithms that can learn value functions without actions. So we have some papers on developing that, and in this VIP work, we extended it to the visual domain and then learned this implicit value function from human videos. So once you have that, what should you expect? You should expect on the optimal demonstration, value should be monotonic. So this embedding distance should monotonically decline as you go through the video, right? And by purely depending on human videos and without any robot fine-tuning, this is indeed what we see in practice on these robotic tasks in the real world. And in simulation tasks, even with a human hand, we also see very smooth and progressing value curves. And whenever there's a bump, you can actually see that's when the robot's actually somewhat executing a suboptimal action, like moving a hand away from the hammer before hitting it, right? So why is this useful? Like I alluded to, you can first of all use it for planning. You can use a dynamics model or the ground truth simulator if you're in simulation to plan a sequence of actions that maximize the value. And you see that using our model, you can plan with much higher success rate and using baseline representations that do not encode value in its representation. And as you scale up the search budget, right, and searching for more action trajectories, the performance steadily improves, meaning that the representation space is smooth enough for trajectory optimizer to exploit. Whereas for the baselines, if you search more, you actually do worse, meaning that there's a lot of local optima in the embedding space that doesn't actually correspond to making more progress in the task. Then we also extended this method to the long horizon imitation learning, which is the idea that value functions are supposed to be monotonic for a short horizon task because we train it that way. So whenever it's not monotonic, when you apply this to a long horizon video, then we can use the divergence from monotonicity as natural signal for when subtasks might have occurred in the video. So using this method, we can segment robot videos without any supervision on the robot data and to segment long horizon imitation learning to make it much easier to learn. And crucially, once you can decompose videos like this, then you also get some sort of compositional generalization. You can at the test time solve the task in different sequence. And this work received Eurekaverse Best Paper in Robot Vision finalist, and the first author, Charles, is also on the PhD market this year. Yeah. And I was serving as a senior advisor on this project. Yeah. And then, like I talked about, we also want to do real world reinforcement learning. So recently we have a preprint using the VIP idea, but overcoming the fact that if you only train value functions on human videos, it's likely to be optimistic because human videos don't contain a lot of failure. So by some minor modification to the algorithm to push down the value for failure state, we have taught a spot robot to automatically explore in the real world and use reinforcement learning to learn how to open the drawer. So you see as the time lapse goes on, it's opening more and more successfully. And at the end, it's pretty much always succeeding, right? So this is a line of work that I have developed exploiting temporal structure in human videos as a learning signal for robots that can be applied to diverse downstream applications like planning, reinforcement learning, and also offline imitation learning. So to the final portions of the talk, let's take a step back and think about robot task specification for a second. So far, the universal value function from VIP that I presented takes an image goal observation. But this observation also needs to be in the same scene as the robot task. So this is perhaps not the most intuitive thing to provide, and often it over-specifies what the task actually is. Like here, we just care about perhaps putting a watermelon on the plate. But if you look at the goal image, it's not clear whether or not the task was just to put the watermelon on the plate or put it exactly in that position in the plate, right? And so sometimes then the robot will learn, not so great behavior because it's optimizing for the wrong objective. So what if we can do something more permissible, like a language goal that can more broadly capture human intent and how we want to communicate to the robot? So can we learn some sort of universal value function that now takes in language specification? So that's the extension that we did called Language Image Value Learning, or LIT, published in ICML 2023 last year, where we essentially extended VIP to be multimodal. So now instead of a single encoder in image, we have a multimodal encoder that also encodes a language goal. And now the embedding distance is computed between the image representation and the language representation. So this has a lot of connection to CLIP, which I won't go over here, but essentially the idea is that VIP can be thought of as a temporal extension of CLIP-style contrastive learning objective. And by combining them together in a single objective, it's actually quite effective at learning language condition robot values. So here are some examples on unseen robot videos at test time, right? So now instead of an image goal curve, you also get a language goal curve where you see as the robot is solving a task of put the water on the lower shelf, you see that embedding distance declines. And again, here is open the toaster door, right? You see that it's able to make up or figure out when the progress for the task has occurred. But if you look at these curves, you probably realize it's not that smooth anymore, right? And that's because when you have a limited set of language annotated human videos, your generalization is capped by that. So in the lift work, we showed you can actually fine tune your embedding. Right? So this is, there are different checkpoints in fine tuning. You see that you can make them more and more smooth and make the image goal and the language goal more aligned, showing that you can continuously make the universal value functions better with more robust data. But I still think that's not really desirable because at the end of the day, the generalization of this kind of method will be limited by language annotated videos. And for fine tuning, you still have to pretty much do the training objective again, right? So recently, I've been taking a step back and just looking at and thinking about value functions more holistically. I'm thinking about how can we make this really powerful source of learning signal for robots in the real world more easily attainable. So I'm looking at value functions. So this is, a simplified version of a Bellman equation, if you will. So typically how we train value functions is by treating it as a, feed-forward neural network, where all the knowledge about what a value function is and, things like Bellman consistency are distilled during training time. So you have to train a model to behave like a value function in order for it to be a value model. But is feed-forward value learning too limiting in practice? So what do I mean by that? So in all of my work like VIP or LIV, we never got the optimal value function. Right? We just don't have the data. We don't know that whether or not it's actually optimal and how suboptimal the approximation is. But it didn't prevent it from being helpful and it can guide robots to learn in the real world. So if all we care about is just having some model that can spit out task progress faithfully so we can guide robots to learn in the real world, is imposing this structure at training time too limiting in practice. Because if you want to train a model this way, then presumably you won't be able to leverage pre-existing models for training on a lot of internet data that don't necessarily are optimized for value at the training time. So to answer this question, in a very recent work, we investigated framing value prediction as a vision language model test time inference problem, showing that we can take a pre-trained vision language model such as Gemini or GPT-4 without any fine-tuning, of course, because I don't have the ability to fine-tune it, just in context, formulate value prediction problem in a nice way so we can elicit zero-shot and a few-shot value prediction capability on a lot of robot and a lot of tasks without any task-specific supervision. So really like making a step towards the goal of universal value function that can guide any robot to solve any task. So how do we do this? So mathematically, what we did is that, first of all, this operates in a batch setting where you have a trajectory or partial object trajectory O1 to OT that's fed in all at the same time to the vision language model, plus a task specification L task that could be a language annotation or even an image, right? But you don't present the frames in the temporal order, but rather you present them in a shuffled order to the vision language model. And asking the model then to predict the values of all the shuffled frames one by one. Right? So this is mathematically what happens for each individual prediction. To predict the value for shuffled time step t, we have all the observations on all the predictions up to that point. So it's a really like an autoregressive value prediction framework, right? And with this way, if this works, right, then perhaps we can also do in-context learning on top of it, meaning that not only we have the query video in the vision language model's context, we also can provide additional examples at test time, observation and value pairs, and just permute them so that value model, so the VLM can use that additionally to make better predictions. So far I haven't explained why this works at all, but this is the mathematic formulation. And now let's get into a more pictorial representation of what's going on. So you have your video, you have your language description, you shuffle them in random order, you feed all of them to the language model, and the predictions are made one by one. So there are two things that's really important. One is input shuffling. The second one is autoregressive prediction. So in practice, we find if you present the original video as it is to the vision language model, then vision language models today will hallucinate nonsensical values, meaning that because it saw a temporally coherent video, it kind of hallucinate and just generate monotonically increasing values, even if the video you presented were a failure trajectory, right? I think this, my hypothesis for why this is happening is because at pre-training time for vision language models, it's largely pre-trained on tasks like video captioning, or video tasks where you look at a whole video in the temporally correct order and try to do some summarization on top of it. So if you ask it to do value prediction, but you present the video in a way that it's really used to seeing, then you would just ignore the task it's trying to do and output nonsensical values. But when we shuffle it, we break up the temporal correlation and actually force the model to look at each frame individually and do the prediction. So in the paper, we have a lot of analysis and ablation for this behavior. But second, why is autoregressive prediction really important? So one way you can use VLM for value prediction, just querying them independently for each frame. But we call that value functions for a trajectory need to be self-consistent, right? They need to be related to each other via something like a Bellman equation. But since VLMs are not trained like that, if you query them independently, then the values for two frames in the same video could have very different scale. They're not self-consistent. But if you formulate the problem this way, autoregressively, then once the model has predicted a value for the first frame, the first shuffled frame, let's say 100%, then when it's predicting the value for the second frame, then it knows that it has already predicted, oh, for this frame, it's 100%. And so for the second frame, because the model thinks it's coming before the first frame, so it will just predict the number that's lower than 100%. So kind of imposing this, consistency for value along your trajectory automatically just by posing the problem in an autoregressive manner to the VLM. All right, so this is a very simple algorithm, and it surprisingly works pretty well on zero shot on a lot of different robot videos and tasks. So here's the raw value predictions once you shuffle the video back, and you can see that on diverse trajectories from very different viewpoints, and even like a navigation video, the model can zero shot generate meaningful value predictions, right? And later we show much more long horizon tasks like shirt hanging, doing laundry, and we also have videos where you just apply the model zero shot to now wrist view camera and even fisheye distorted views, and the model again does fairly well and can discern progress and the lack thereof in videos, right? So let's look at some concrete example. So here is a video taken using the universal manipulation interface from Columbia and Stanford and TRI. And I'll play this video manually so you can see what's going on, right? So as the video is progressing towards the cup, first of all, it went up. But do you see in here, for a very slight, maybe 2 frames, the action is suboptimal, where the operator actually moved the gripper away from the camera. And the model is able to detect such suboptimality with a dip in the progress curve, even though when the model was seeing this video, it's in complete shuffled order.
Why are the values so discrete, 0 or 50?
Yeah, so sometimes it's just outputting discrete numbers. Sometimes it's outputting like 79, 45. So it just sometimes the model behaves discretely and sometimes it doesn't. And I didn't really control for that. And here's another example of where it's able to detect failures, right? So as the model is going to turn the doorknob, okay, it's going up. But once it slips and didn't solve the task, it went back down. Right? So this is just to showcase it's possible to get dense prediction from pre-trained VLMs and use them in meaningful ways for a lot of downstream applications. And I think before this work, universal value function has only been qualitatively studied, like in my prior work, where I look at the curves and see, oh, it's smooth, it's not smooth. But in this work, I really wanted to make that more scientific. So beyond the large scale evaluation, which I'll talk about, the first thing I did was to introduce a metric to evaluate the prediction quality. If you think about traditionally how you would evaluate a value function, maybe you'll train a robot model with it, right? But if you're trying to evaluate hundreds of tasks, hundreds of robots, that quickly becomes not scalable. So a metric that we introduced in place is this thing called value order correlation, or VOC. So the idea is that, okay, it's really difficult to evaluate a value function globally, but on expert trajectories, we know that values should be monotonic by construction, right? So on expert trajectory, we can take the model's outputs, value outputs, and sort them in ranked order, and then compare the correlation with the ground truth time step order. Because on the optimal trajectory, the ground truth time step order is monotonically increasing time. So we can use this on expert trajectories as a way to measure how good value functions are, at least on good trajectories. And then what about the bad trajectories? Well, we call that in the generative value learning framework that I'm proposing, the videos are presented in shuffled order. If you have a bad trajectory, like for example, your robots are just waving its arm, not really making progress, then if you shuffle that video, then you kind of lose all information on how to shuffle it back, right? For optimal trajectory, except when the optimal trajectory contains loopy behavior, it's very likely that every single observation you see is monotonic. So if I give you 10 frames that's shuffled, you have the ability to shuffle it back. But if I present to you like a bad trajectory, you really can't shuffle it back. So this correlation could really be anything, right? So the hypothesis here is that using this as a metric, we can discriminate good versus bad trajectories at a very high level, right? And that has a lot of downstream applications. And using this just an expert trajectory is a good way to evaluate how good the value models are. So first, we did a large-scale evaluation on 50 data sets from the OpenX collaboration across many institutions. And the main comparison is my prior work LIV that trains universal value function from human videos. So here is the results. It's like a histogram over all the individual trajectories in OXC data sets. So it's not the entire data set. It's like from each data set, we sampled 20 trajectories, aggregate them all here. So recall that OXC is mostly demonstration data set. And a good value model should be monotonic on demonstration data set. So you should see most of the weight in this histogram on the right if the value model is good. So that's what you clearly see for the new method GVL, where most of the value prediction correlation is like above 0.5, many of them even above 0.75, meaning that it's almost perfectly reconstructing the original order in the video, even though it has to look at shuffled videos. Whereas for my prior method LIV, it's only trained on human videos, which is much more limited. So the prediction is like much more random across the board, meaning that it cannot zero shot generalize to arbitrary robot data set that's in the academic community, right? And then to really stress test the method of Google DeepMind internally, we also have a new data set of 250 bidextrous manipulation tasks. That's much more difficult than the ones you see in OXC. And then here's the results on Aloha 250. And now we are also incorporating in-context learning, where we feed some sample observation value pairs from the same task as context to see whether or not I can improve the prediction. So you see that zero shot, which is the the blue bars, on average, it has roughly very weakly positive correlation, right? Compared to the OXC data set, you can clearly see the bars are shifting to the left. But with one shot example, then the prediction actually becomes a lot better shifting to the right. And we just didn't stop at providing one in-context trajectories as examples. We scaled it up substantially by feeding in 1, 2, and 5 in-context trajectory examples. And the average value order correlation on these Aloha tasks steadily improved. And just to understand the scale of how many pictures we're feeding in the context, if you have 5 in-context trajectories, that's more than 150 frames in the VLM's context, in addition to the video it has to predict values for. Right, so this is like, to some extent, one of the first multimodal in-context learning results in robotics as well, where we showed value predictions can really benefit from more test time inference. And I think that sort of makes sense because traditionally you would train a value function better if you have more coverage of the state space, right? That was sort of a theoretical requirement. And here you can see as like a way of trying to do that at a test time of feeding observation and value pairs in the context. And we can improve from weakly positive, like 0.3 linear correlation to almost like 0.65, close to 0.7. But I think the in-context learning capability really provides a lot more flexibility than what I had just shown, right? You could theoretically also just feed the observation of values for even a human demonstration and see whether or not that also helps with robot prediction. And the answer is surprisingly that it kind of also works out of the box, right? So that's like a subsampled sequence of the human videos of human pulling out the phone from a purse. And then we use that as the context to predict the values for robot video. So you see that the performance is roughly sandwiched between doing zero-shot prediction and doing one-shot prediction, where the examples are coming from the robot side. But this is very powerful because imagine now you have a new task for which you haven't collected any robot demonstration. Then you could just provide a lot of human videos, you solving a task, and use that as context, which have a good on-the-fly value models that you can use to guide robot learning. And we also explore that cross-task and context learning, where you can use videos from another task, and that again improves performance. So you see with this test time improvement capability, there's a lot of flexible ways to make something really essential like value functions a lot better, where with the previous paradigm of doing all of that during training time just doesn't provide you, right? And I think with something that's general like this, there's a lot of new applications we can explore. So one thing we did is this thing called dataset quality estimation. So if you went to Coral or interested in imitation learning, you know that these days a lot of people are training large imitation learning models on a lot of robot data sets. But how do we decide which robot data set that should go into the pre-training mix? It's totally, again, a graduate student trying different things and playing. I mean, this OpenVLA paper, it's really nice that they actually made a footnote on how they came up with it. And they noted that data set they thought was good, which they gave 10% weight. After they trained the model for 2/3, they realized it's actually really bad. So they manually removed it for the last 1/3, right? Just showing that when we scale up imitation learning, there's a lot of data set quality consideration we have to do. So how does generative value learning help here? We call that the value order correlation metric is a good way to tell apart good trajectory versus bad trajectory, right? So if you compute the average value order correlation on the entire data set, so here's actually a subsample set of data, and you can rank all the data set that you possibly want to train on to get a ranking of, okay, what data sets do the VLM think are roughly monotonic and contain demonstration behavior, which ones do not. And here's a subset of the list, and the whole list is in the paper, you can check it out. And these make a lot of sense. If you look at the RT1 data set, it's human collected teleoperation, doing a bunch of pick and place tasks, and the same goes for bridge. That's why they have really high average correlation. But if you go to the bottom of the list, like RoboNet, this data was actually collected by having robot doing motor battle, just randomly exploring the workspace and trying to touch objects. You can imagine if you shuffle that particular video there, the model or you probably don't have any way to recover the original structure, right? Because the actions are totally random. And then you see that Droid data set also has something here. Meaning that we can actually automatically discover what data sets are good for doing just vanilla imitation learning and whatnot. And we can use this as a way to guide future large-scale imitation learning. And the second application, once we show that this is a good method to discriminate good versus bad trajectories, is that naturally we can, within a data set, filter out failure trajectories, right? So on these simulation tasks, we collected about 500 successful, 500 failure trajectories. And then you plot out the value order correlation for all of them. You see that the distribution is clearly different. So the way now we can use this as a success detector is by determining some value above which you declare a trajectory successful and below which you say it's unsuccessful, right? So this is like turning value prediction into success detector. So here we compare, so that method we call GVL-SD, SD stands for success detection. We compare to using the same VLM and feeding in the same video, but rather doing value predictions first, we just ask the model yes or no. Did this trajectory succeed? And
I
you
have
see
to
that.
warn you, this unfortunate room is gonna kill the screen at 5.
Oh, okay. Yeah, we're almost done.
Okay, good.
Yeah. So you see that not only the accuracy is a lot higher, we also have much higher precision. Whereas the baseline really systematically favors outputting successful trajectories, maybe just because VLMs like to say yes, right? But if you shuffle it up and make the model use more compute, predicting more things, and using that output, then do success detection, you have much higher precision and accuracy, right? And then you can use those success detectors that we just showed to do filtered behavior cloning on mixed data quality. And using filter from our method is much better than using the filter from the baseline that brain success detection as a VQA, visual question answering problem. And then finally, previously I manually set it to 0.5. We also tried many different values and see compared to not doing filter at all, which is negative 1.0, do we consistently see performance improvement? So the answer is yes, right? It seems that, for this data set, the sweet spot is 0.5, because after 0.5, then your data set becomes too small, limiting generalization. But this is to show the performance improvement you can get from using generative value learning success detection capability could, at least in this data set, is somewhat insensitive to the exact threshold you set. And then finally, just quickly, we also use the dense values from the method as rewards to do offline reinforcement learning. So here what we do is to combine diffusion policy with offline RL. So we upweight transitions that the model thinks is good. And we can solve a bunch of diverse tasks whenever you see the average correlation is good. So when the value predictions are average good, we can expect some performance gain. But we also show on some tasks, value predictions are bad. So when the values are bad and you do offline RL, you actually can regress in performance, right? Just to showcase there's still a lot of improvement to be done. But I think this really shows a new way of doing value prediction that's really scalable. And we have an interactive website with a lot of examples, and I encourage you to check it out. Right. So the conclusion is that here we introduce a new test time paradigm for doing universal value functions, and we demonstrated multimodal in-context learning capability with a lot of downstream applications. But I think this opens up a lot of new questions than it answers, right? Like, why does this thing work? And whether or not this kind of capability can continue to scale as the base models get better. And I think those are really interesting questions to explore in this slide. So just to conclude the talk, I presented you a high-level overview of some of my work on doing scaling up foundation model supervision for robot learning. We explored using large language model to automate sim to real, using human videos to provide values at scale. Finally, a new test time way of doing universal value predictions from vision and language models.